Hello everyone, Chicken Puck here. Today we're going to be looking at Floquet theory, and then I'm going to simulate it using QuTiP a bit later. Let's get started. Let's start with a time-independent Hamiltonian. So if phi n is an eigenstate of H, then applying the Hamiltonian just gives us the same state multiplied by its eigenvalue, which is an energy eigenvalue. Now we can solve the time-dependent Schrödinger equation. So as you can see, the state itself doesn't really change, like its shape. It basically just picks up a complex phase defined by its energy value. We see the time dependence is completely dependent on this exponential. If I were to just write h of t here, but now suppose that I'm driving my quantum system. The Hamiltonian itself will change with time, and generally I can't just take a fixed case of a fixed eigenstate and then multiply it by I et over h bar, because the operator governing the system is changing as the system evolves. But there's a very special case. Suppose the Hamiltonian repeats itself every t seconds, this t. So after one period, it's the exact same Hamiltonian. So for example, imagine a static Hamiltonian h0 with a sinusoidal drive. Then t would equal 2 pi over omega. So as you can see, once we apply t and plug it in the sinusoidal drive, we get back out the same sign here. So even though the Hamiltonian is not constant, there's still some structure here. It repeats. The Floquet theorem describes this periodicity. So what Floquet's theorem is saying is that if the Hamiltonian is periodic, the solutions to the equation can be written in this form. You might notice this looks especially similar to our time-independent solution. So putting the periodic case and the time-independent case side by side, so in the ordinary case we have an energy En and a stationary eigenstate phi n. In Floquet theory, we simply have a more like an analog called quasi-energy. We have our epsilon alpha. I've written down quasi-energy. And then coming back here to this equation, this periodic part describes everything happening in the drive cycle, right? So one way to understand the quasi-energy is to see what happens after one period. So as you can see, I've started off with the original equation, then I added the plus t. So then by periodicity, after one complete drive period, a Floquet state comes back to itself up to some phase. So this looks very similar to what an energy eigenstate does under ordinary time evolution. That's why the epsilon plays an almost energy-like role. So now we're going to connect this to QuTiP. So this is the example we're actually going to simulate with QuTiP. So QuTiP's example uses a strongly driven two-level system. So these two terms form the static Hamiltonian, h0, and then this term is our periodic drive, which is along the z direction with an amplitude a and an angular frequency omega. So here our t is 2 pi over omega, and because this drive is sinusoidal, the entire Hamiltonian repeats the 2 pi over omega. So we have the exact condition needed for Floquet theory. Okay, let's start coding now.
Hey everyone, it's Chicken Puck again. So we are on the Google Colab coding system. So if you're not familiar with this, basically allows you to run code and you can have it on your browser. So first thing I did here was install QuTiP. So you can go on the documentation if you want to. Now I'll leave that link below in the description. So what we're going to do is simulate the exact periodically driven two-level system we just discussed on the board. So what I'm doing here is just importing the NumPy and the QuTiP tools that we need. So the basis will give us the computational basis states that we need, and the sigma x and sigma z, of course, are just the Pauli x and z operators. So FESolve is QuTiP's Floquet Schrödinger equation solver. If you are unfamiliar with any parameter, you can always hover over it, as you can see more details about it. And then the plot will allow us to visualize that result. So now what we're going to do is define our parameters, and as you can see, this delta term will control the x term in the static Hamiltonian, right? And the epsilon 0 term will control the static z term, okay? And as we went over earlier, the a is the amplitude of the periodic drive, and then omega is just the angular frequency of that drive. So these are the parameter choices used in the QuTiP Floquet solver example. I will leave that documentation below. as you can see here, we create part of the Hamiltonian that does not depend on time, which is why it's static and it says H0. So in the code, we see that the sigma x and the sigma z are here. And as earlier stated, those are going to be the poly x and z operators. So this line directly implements the static part of that two-level Hamiltonian. So now we have to look at the periodic drive. So here we create the time-dependent driving term, which is the h1 of t, as we defined earlier. So QuTiP defines this as a list, and we can see that with these brackets here. So if you are familiar with Python, this will create a list, okay? So the first entry is the operator, and then the second entry is the time-dependent coefficient sine omega t. Then the dictionary args, which we can see is defined by these curly brackets, tells QuTiP that the variable w in our expression is the angular frequency omega, and then we just combine this Hamiltonian together with h0 and h1. So now, this h is the complete periodically driven Hamiltonian that we wrote on the whiteboard. So the initial state is here, and we are starting in the computational basis state 0. So in QuTiP, when we define this, we mean the first basis vector of a two-dimensional Hilbert space. As I mentioned earlier, if you are unfamiliar, you can always hover over the function and then see the information there. Unfortunately, I did it twice, so I just deleted that cell. So now we are going to calculate the period of the drive. So earlier we wrote down 2 times n pi over omega. So since we chose omega equal to 2 pi, this gives us t equals 1. And that is the important Floquet condition. So after one period, h of t plus large t equals h of small t, the Hamiltonian repeats exactly. So here what's happening is we're creating a time list, which we want QuTiP to evaluate, right? So what I'm doing here is simulating from 0 to 2.5 periods using 101 time points. So we're basically watching the system through multiple cycles of the periodic drive. Now the last step pretty much is to run FESolve, which as I stated earlier was the Floquet Schrodinger equation solver. We pass in our Hamiltonian, we pass in our initial state, we pass in the time points and the period t, and then I'm also passing in the sigma z, which is the expectation value operator. So what's happening is at every time point, QuTiP will calculate the expectation value of z of t equals the expectation value of psi of t bar sigma z bar sigma of t. So what we're going to do here is finally plot the z expectation value. So as you can see, we started in ket 0. So at time 0, we have +1. So as the periodic Hamiltonian drives that qubit, the state evolves from ket 0, and the value moves downward and then back upward. So what we're seeing here is the qubit state evolving under a periodically driven Hamiltonian. So one important distinction is that the oscillation itself isn't what makes this Floquet theory. The two-level systems can oscillate in lots of situations. What makes the Floquet theory applicable is specifically the h of t plus t equals to h of t. So the Hamiltonian repeats in time, so we can use that Floquet structure rather than treating the problem as an arbitrary time-dependent Hamiltonian. In closing, this was a very simple example of Floquet dynamics. We started with a periodically driven two-level Hamiltonian, calculated its period, passed that structure into the FE solver in QuTiP, and then watched that Z expectation value evolve over time. And that whiteboard we had earlier gave us the theoretical statement. And now we've used QuTiP to actually simulate the dynamics of a system where that Floquet formalism applies. Thank you for watching.